Okay, hello everyone. So welcome to this guest lecture by Professor Maurizio Filippone, so from Eurocom. And he's going to talk about functional priors and Bayesian deep learning. So please, go ahead.
Right. Thanks a lot, Marcus. It's awesome to be here today at the Alto. It's great. Thanks, Aki, for inviting me to be opponent for the defense tomorrow. And it's great to be here and give a talk in this place where there has been so much good machine learning happening. So today, the content of my presentation is about Bayesian deep learning and some of the recent work we've done to try to make it work in the best possible way. So as a person working in Bayesian statistics, I've always found that when you have a model and you make it Bayesian, you have some advantages in the fact that you can introduce prior knowledge, do model selection, you get good quantification of uncertainty. And usually the performance is not worse. Sometimes you have to invest a bit more in the, having to do a little bit more work, but then it pays off. And unfortunately, for a lot of the deep learning models that people have been working on, like big convolutional neural networks that do so well in image classification problems, we were struggling to get anything decent out of these, approximate Bayesian inference approaches to deep learning. So we looked into ways in which we could counter this problem and come up with something that would work actually. And this is a joint work with my PhD student Bayesian that has done tremendous work in this space, with one of my former PhD student and then postdoc Simone, my former postdoc Dimitris, and my colleagues and good friend Pietro and Edwin. Edwin is currently at Data 61 in Sydney. All right, so what I will talk about is mostly about these priors for Bayesian neural networks, which is what we thought that would be the problem of why we could not get good performance out of treating neural networks in a Bayesian way. But I also wanted to, I'll spend maybe a few minutes also on something else, which is, so when I think about Bayesian neural networks here, in this first part, it's going to be mostly supervised learning, whereas you can also think about neural networks in a configuration which is an autoencoder. And again, it's a neural network. And the common trend is for people to do variational inference, so variational autoencoders. So this is a very popular way of doing unsupervised learning, so generative modeling, representation learning, compression, you name it. But not many people, and we believe because of this problem of how to choose priors for neural networks, not many people have actually looked at, just take an autoencoder and make it Bayesian and treat it using inference methods that can be even beyond variational inference, all right? And then I'll draw some conclusions at the end. All right, so I'll go briefly on this. So we know deep neural networks are so powerful. They've achieved impressive performance. Yes?
Do you have a speaker on?
Not me. Maybe I should lower this. There is echo maybe coming from this guy. I'll just... Yes, yes, it keeps coming back, but I'm not sure if it's because here I'm muted. Yes, still coming back. I have some echo, but I'm not sure where it comes
from that direction. That there's also speaker there.
Maybe this one.
Does someone have experience with this?
Hello, hello, hello.
Yeah, now it went away.
Is it? No, it's still there. It seems like it's coming from my laptop, but yep. Hey. I don't know. This doesn't have any volume anymore, so I don't know.
Yeah, it has to be here.
No, let's not switch off the projector.
Now good?
Hello? No.
But it sounds like it's coming.
Yeah, but how can it come from here? There's no volume and there's no microphone, so if it doesn't bother you so much, maybe I can continue.
Yeah, continue.
We're not sure. Everything is off, but sound is coming from somewhere here.
Please continue.
Yes.
Sorry.
Okay. No problem. So, but yeah, because it's coming from here, the sound, the microphone. So, Marcus, do you have any?
Zoom is saying that echo is audible, but okay.
Okay.
I guess we can compromise that.
right? One of the problems with deep neural networks, however, is that it's difficult to, well, it's important to, we have these very flexible models that achieve very good performance. It would be great also if these models had the capability of knowing when they don't know in making predictions, so that, having some sort of notion of uncertainty, so that it's possible to, again, knowing when the model doesn't know, so maybe we need more data, or out of sample data from out of sample distribution to be able to characterize when this data is really so off from the training data that we have no idea, so we have large uncertainties and so on. Well, obviously, if you just do point estimates, this is not gonna happen. So usually, what people do, they just optimize some loss, and there's some regularization, obviously, early stopping, dropout, L2 parameter regularization, you name it. Another way to, one way to embed this notion of uncertainty is just to say, well, let's just have distributions over the parameters, and then in light of data, we just obtain a posterior distribution over the parameters. So we start from a prior, and then we just use Bayes' theorem to get posterior as the multiplication of the likelihood times the prior. Obviously, if we want this to be a proper density over W, we need to make sure that this product here is properly normalized, and this is the usual difficult problem in machine learning when you try to do things in a Bayesian way. But if you can characterize this posterior, then you can do something which is magic that not many other formulations can do, which is making predictions which are parameter-free, right? So when we have these predictions for test data, then you see that somehow these predictions will be conditioned on values of parameters, but now we integrate out, we take an expectation under the distribution, the posterior distribution. So as a result, we get predictions that are solely based on the previous data and the test point. So these parameters magically disappear because actually we're accounting for an infinite number of parameters that are compatible with the data according to this posterior distribution. And now we're weighting them in a way that we make an infinite number of predictions and we average, right? So this is quite nice. So people have been talking about Bayesian neural networks since the 90s, at least. I think there might be even earlier references than the one in Mackay 1992. And 96, Ralph O'Neill has done this influential work on Bayesian deep nets and or connections with Gaussian processes. So you can view Gaussian processes as shallow neural networks with an infinite number of layers. Infinite number of neurons. And then there's this connection with the obviously deep neural networks and deep Gaussian processes also in that work. And I think the first practical implementation of approximate inference for deep nets is this version here of Graves 2011. I think it was ACML or NeurIPS paper 2011, where he proposed mini batch variational inference for deep nets. So in this formulation, he was able then to do stochastic optimization of the parameters of the distribution, the posterior distribution over the parameters. So to do variational inference. And at the time, this is quite interesting because at the time there was no automatic differentiation. Well, there was, but not readily available the way we have it now, like with PyTorch and TensorFlow. And TensorFlow was released at, I think there was a talk at NeurIPS 2015, actually, when the first time they announced the release of TensorFlow. And from there, I think a lot of things changed because now the development of these methods really can rely a lot on automatic differentiation. So you don't need to hard-code certain computations of the derivatives as we used to do. So I see a lot of young faces here. When I was your age, probably, well, I spent a lot of my time just implementing derivatives of objective functions and debugging them, especially. So the development loop has really increased massively, I think, from here. And now, already a few years back, it was already sort of this idea of being able to do stochastic optimization for these models was already out there, right? And not long after, there was also some influential work on mini batch MCMC sampling. So this is stochastic gradient Hamiltonian Monte Carlo. Around the same time, also EYT and Max Welling were doing the stochastic Langevin dynamics paper, again with the stochastic gradients to do some sort of sampling from posterior distributions, right? And this is quite, the mini batch aspect is important because, again, operating on mini batches allows us to scale to a large number of data points. So at the same time of, well, 2016, then there was I would say, the first ever practical approach for approximate Bayesian components. So if you would take a convolutional neural network, you would try this 2011 mini batch approximation. I mean, for small architectures, this would work. But as soon as you would go beyond the LeNet, you would try it on bigger data sets with more complicated architectures, this would completely fail. And when I say fail, I mean that the posterior distribution, the approximate posterior distribution, will collapse back to the prior. So we spent quite some time in my group trying to figure out why. Well, an easy reason I can give you is that if you think about the variational objective, you have one part, which is the expected log likelihood. And that's typically a sum of as many terms as the number of data points you have. And then you have a regularization term, which is the KL between your Q and the prior. And that typically is a sum over as many terms as the number of parameters. So if you have a model with millions of parameters and only a few 100,000 of observations, then obviously that regularization part is going to dominate. And so the posterior will tend to really like to go back to the prior. And so we found different ways to kind of try to fix that problem. But if you think about this approach where you just do dropout and then at test time, you just do again dropout at test time to get some uncertainty quantification of your predictions, this is really very easy to do. And that has connections with the with variational inference. So that I would say is, I couldn't find anything before that could really do something which is approximate inference for convolutional networks on reasonably sized data sets and architectures. Also around 2016, I think it was first workshop on Bayesian deep learning, again, organized by Yaringal and Zubin Karamani. And I mean, one of the things that I think, why don't people just do Bayesian deep learning these days, right? So why don't people just use Bayesian deep neural networks so much as we would think that they should? And one of the urban legends, I think, is that it's slow compared to optimization. I mean, if you talk to people about the fact that you're working on MCMC or using MCMC, people would say, well, that's too slow. You know, I don't like MCMC, it's too slow. And I think this is to some extent true, but now these days that we have these options of doing mini batching, maybe we need a lot of iterations, but the cost per iteration is not going to be as bad as we think, because also when we do optimization, we rely on mini batches. So really the complexity of one iteration is not going to be much more. It's just that maybe we need a lot of iterations to be able to explore the parameter space. But on the other hand, it's, you know, if we want to do convergence statistics and so on, we typically need parallel chains. So some of it is also parallelizable. So maybe it's not that bad. Cumbersome to tune implement, you know, people that don't want to spend too much time optimizing their MCMC sampler. Well, I don't know if you've read some of the papers where, you know, the optimization also, if you want to optimize a convolutional neural network, there are all this magic going on about how you choose step sizes, how you anneal step sizes throughout the optimization and so on. Even in the Monte Carlo dropout paper, if you go to the appendix, I think, there is a recipe on how you have to tune the step size to make things work. So there is design there too. And so it's kind of cumbersome to tune this kind of optimizer too. So I wouldn't say that things are so bad for MCMC at this stage. But the normal legend, I think, is that it doesn't work. So as I was saying, you know, this, when we were trying to do variational inference, it's really, really hard to make it work for like big models. And so a lot of people try to come up with alternatives. I mean, if you work in this domain, you know, probably ensembles, deep ensembles. It's a very influential paper that, you know, people maybe use a lot these days, also Monte Carlo dropout. But this was like, people have tried so much that at some point people started to think maybe there is a problem with the Bayesian posterior when we work with deep neural networks. And so some groups have started to even question the optimality of Bayes for these kind of models, which I think is kind of sacrilegious, if you ask me, because there is nothing wrong with the Bayes theorem. You know, Bayes theorem is a recipe to turn a conditional distribution into the reverse, right? So you have a prior, you turn it into a posterior given data, right? So there's nothing wrong with that. So the wrong thing that can happen is the ingredients that you put into this into this base formula. And the ingredients are the likelihood. But I mean, given a model that you want to use and the type of data you have to model, it's kind of given. You know, there's not much, well, there's maybe some room to make a better likelihood, but you know, that's pretty much what it is. And so what is the other ingredient? Well, it's prior. And the problem of choosing priors has been massively overlooked in the literature. So in this work, we tried to actually come up with a better way of, well, with a good way to choose priors for Bayesian neural networks. And the problem is that it's very difficult to specify what a good prior for neural networks is. Why? Because, well, usually when you don't know what to do for a distribution of a parameter a priori, what you say is that, oh, I'm just going to put a 0 standard normal prior, 0 mean, 1 standard deviation, and I'm good. Or you say, I don't know, so I put a large variance, right? And this is unfortunately a terrible way of operating, because the effect that these priors have in the output is very marked, but it's also very unpredictable. And so, and the reason is that these models are highly nonlinear. And so the way the computations are propagated throughout the network are quite complicated. It's a composition of functions. And so as soon as you start choosing these distributions, you can get a lot of massively varying weights that you know, produce outputs which are completely crazy. And another way, you know, you can think about not to make it explode by this kind of 1/, cardinality of neurons coming into a neuron. You know, this is kind of Xavier initialization kind of ideas. You can start thinking about priors that do that so that you don't have outputs that explode. You can try that, but still, there is a very difficult, it's very difficult to understand what kind of functions you can model when you make these choices, all right? And so from now on, I'm going to refer to this as the functional prior. So I'm going to have a prior over the parameters, and the parameters are propagated through the network, all right? And I have a way to compute f given w, right? Where f is the output of my neural network. And for simplicity here, I just put everything probabilistic, but you can think of this as if it's a deterministic neural network, it's just a delta on the evaluation of the neural network for those parameters, okay? And I omitted the inputs for simplicity. And what this is just a prior then over the outputs, right? Which is, again, induced by the choice of P of W, right? And so, so this is a simple example. I think this is a 3-layer neural network. So I have a video here open. So this is a small animation. So here I have a control over the prior standard deviation for the weights and also prior standard deviation for the biases. And as I play this video, you can see that as I move the prior standard deviation over the weights and the prior standard deviation for the biases, I get some effect on the functions that I can model a priori with this network, which is quite difficult to predict. And also you can see that the kind of functions that I'm modeling mostly are flat. And they may have this kind of weird behavior around 0 here, just because of the way the parameters are, the priors are parameterized. But you can see that mostly this is the kind of functions that I represent a priori. And so you may think, well, if you have some data that has some periodicity, or you know that maybe there is something going on, there is some certain variance that you would like to model. I mean, this is really a priori. Having these priors is quite bad. Maybe these are quite pathological cases. So maybe we want to move away from these and try to do something better. And so this effect of pathological priors has been studied a lot already in Radford Neal's paper in 1996. There is a beautiful paper by David Duvenot, 2016, I think, where they do beautiful illustrations of this effect for deep Gaussian processes. So this is not a new problem that people have looked into. But the problem is how to actually now try to do something better for the priors that we can choose for the parameters so that we get something which is more sensible. And so as a person working a lot on Gaussian processes, for me, an easy way to specify a prior over functions is through a Gaussian process. So with a Gaussian process, we usually can choose a mean function, a covariance function, and the covariance function and the mean function encode some properties of the functions that we think that could be good in our problem a priori. So for example, if we choose covariances so that our functions that we draw a priori from this prior can be infinitely smooth or have periodicity, you name it. And so this is kind of a, let me pass it, an interpretable way of choosing these priors, okay? Although we're not doing interpretable machine learning here. But you know, when you then construct these priors, then the realization of the function at different inputs is going to be jointly Gaussian, and it's going to have a structure, a covariance structure, which is determined by the choice of this covariance function K. All right. All right. And so now, if we do this, let me play this video here. This is what we know quite easily, that the covariance we can parameterize with the parameters like length scale and prior variance, so that when we play around with these parameters, we have a very direct way of understanding what the functions do a priori. And so this seems to be like a better way of specifying these priors in function space. And so now the question is, how can we impose these functional priors that we may like through Gaussian processes? But you can choose anything you like. But I'm presenting Gaussian processes just because this is what we did and what we're easily familiar with in order to specify priors. But you can choose any functional prior of your liking. And so the question becomes, how do we make sure that the samples that the functional priors for Bayesian neural networks match what we want, a functional prior of our liking, okay? And so now this is kind of difficult because we're trying to match stochastic processes, so that's already, you know, infinite dimensional territory there, which is kind of tricky to work with. And we don't know the form of this functional prior for Bayesian neural networks. Again, we don't know it because we only know it through, it's going to be a composition of complicated transformations. And so we don't have it in closed form, but we can easily sample from it. So if you draw samples from the prior over W, then you can propagate forward computations and you can obtain functions. So if you do this many times, you can have samples of functions in the output for your neural network. So one first thing to do would be to say, well, why don't we just minimize KL when we have distributions that we want to match? Maybe we just do it through KL minimization. So we would like to maybe minimize the KL divergence between the functional prior for neural networks and the one from GPs. But if we do this, we get an entropy term which is intractable. And so we have to somehow resort to a different way of operating, because again, this entropy term cannot be computed. It can be approximated, but people have tried in the past. Again, David Duvenot's group has done some work on this in 2017, where they were trying to actually approximate that entropy, but it's very unstable and very difficult to approximate properly. So we actually resorted to, you could say, the literature on optimal transport to actually try to find a different way of doing it. And so we came up with this idea, which is quite simple to implement. I mean, it looks maybe a bit complicated at first, but then it's actually not so bad. So we start from the definition of the one Wasserstein distance between two probability measures. And so here I'm calling them pi and nu. And so you can think of these guys as being the distribution or the functional prior for neural networks and GP. And so the calculation of this Wasserstein distance it looks quite strange, because we have a supremum operation here of the difference of two expectations. All right, and these expectations are taken with respect to these phi functions, which are one Lipschitz, and they operate on samples from pi and nu. And so the idea here is that we sample this one Lipschitz, which act as some sort of discriminator. And what we're going to do is to try to apply this discriminator to samples from pi and nu, take expectations with respect to these two distributions, and take the difference. And so we are trying to find the one Lipschitz function that maximizes this difference in expectation. It's sort of similar to what happens in GANs. So we're trying to find the functions that maximally discriminates these two expectations, right? So in practice, we don't need to compute these expectations exactly. We can rely on Monte Carlo, and this is what we're going to do. So we can just sample from the the two distributions pi and nu. And also, in order to parameterize one Lipschitz functions, we can rely on parameterization of this phi function as a neural network with some conditions, so that we impose that this is almost one Lipschitz. Okay, so we do it in a soft way. And so now, because this phi is parameterized using a neural network, we can just do simple mini batching, and everything is sample based. So it's quite easy to actually estimate this Wasserstein distance. And now this Wasserstein distance, remember, now is a function of the prior over the function prior of the neural network and the GP, and the one for the neural network has parameters of the prior, right? So now we can minimize this Wasserstein distance. So we can try to find the parameters of the prior of the neural network such that we minimize this distance. So we have a minimization problem where the objective requires us to do a maximization over phi, right? It's a bit complicated. I have a diagram that confuses even more, right? So we have samples from the GP, samples from the neural network, and now we use this parameterization of phi in order to compute this difference in expectation. And once we do that, then we try to optimize this Wasserstein distance by optimizing the parameters, which I call psi here, which are the parameters of the prior of the neural network. Okay, so this neural network has prior parameters psi. Okay, and now this whole thing can be done in mini batch form, so it's quite easy actually to run it. Okay. All right. So objective is fully sample based, so we can actually match to something else than Gaussian processes. Anything that you can sample from, you can use in this formulation. And again, we can optimize all this with the stochastic gradient optimization backpropagation. So automatic differentiation here helps us to do all the backpropagation to optimize this objective with respect to psi. Okay. Obviously, I mean, now we're matching stochastic processes. So ideally, these expectations should be done in a way that you compute these expectations over this F, GP, and neural network in a way that you do it on the whole input space. Obviously, this is impossible to do because we have an infinite number of input locations. So we just do it in, by sampling from different sets. So we can do uniform sampling if we're in 1 or 2 dimensions. We can sample from the training set with possible some augmentation, or we can just split training test use training test inputs just to enforce that somehow the stochastic processes look the same in a series of knots of our liking. Okay. And then, so once we have optimized our priors so that the functions that we can generate from our neural network look like the GP, now we can then use these priors to do, use data now to do inference, right? And so for that, now we can use any inference algorithm of our liking. You can do variational inference, or what we rely on in our work is the stochastic gradient Hamiltonian Monte Carlo, just because it's mini batching. Is mini batched, so you can just work with any number of data. We found that it works really well, so this is what we use in our experiments. So another interesting thing now is that the prior parameterization, you can go crazy with it now, because you can have a simple parameterization as before, where you just optimize the variances of the prior at each layer. For example, you can make it layer dependent if you like. We can use this hierarchical prior, which actually works really well, which, again, the sigmas here are, so the priors are parameterized with a certain variance, sigma square, and this sigma square is given an inverse gamma distribution with parameters alpha and beta, and now we can optimize this alpha and beta. So effectively, we're working with T distributed priors here, all right? If you marginalize out sigma square, you get the T distribution. But now you can also do something crazier, which is normalizing flow priors, all right? So normalizing flows have been used to do good variational inference, where you increase the flexibility of your posterior approximation. But now we can also try to do it for the prior. and then work with these priors. And then again, remember that everything that we do after this is just MCMC. So this is how the optimization works. Just play this video here. So maybe I'll put it in a way that you can see what we're trying to match. All right. So this is the target GP prior. So you see a bunch of samples in blue. Sorry. And then the optimization starts from something which is a bit pathological, again, flat lines. And as the optimization goes on, you can see that the samples start to look more and more like the samples from the GP. And I think we did this with the normalizing flow prior because it's so flexible that it can really match a GP prior with I think this one was with an RBF covariance, which means that these samples are infinitely smooth and so on. So pretending that, I mean, demanding that the neural network is able to reproduce that is quite difficult, and in general, not, you see that the result is still not perfect, yeah? But there are conditions that you can tell you whether you can approximate. I mean, if you have a neural network with the ReLU, pretending that you can approximate infinitely smooth functions is obviously impossible, right? But this gives you an idea of how the optimization kind of works, all right? All right, so this is just a small illustration of what's going on. If we use some, without data, again, these are the kind of priors that we can sample from the GP. And this, if we fix with these 3 different parameterization I showed you before, these are the kind of functions you get a priori. And now, after we optimize our priors, then you get something which still not that great for this one, for example, but they start to look a bit more like a GP prior. But the important thing to me, even if this prior here is not that great in the middle here, as long as you move away from this pathological situation where your functional priors are completely terrible to model some data, as I will show you in a second, I think already that makes a big difference, all right? And so even if you don't optimize perfectly, you see that now the Wasserstein objective here goes quite nicely close to 0, but here it doesn't, okay? In this other case, obviously it does because we have a more flexible prior parameterization. You can still, as we will see in a second, get something that when you then combine it with data and you try to do a regression task in this case, you still get uncertainty quantification, which is kind of nice and kind of, I would say, comparable with GP, although our job is not trying to do as well as the GP, because now we have a more flexible model, which is not the GP. We have a neural network, but as long as we impose priors that are moved away from pathological situations, I think we're already doing a pretty good job. And you can see that the uncertainties sort of are much nicer than the ones that you can get from not doing any optimization quotes of the prior, all right? So results, just quickly, I just wanted to point out, here we have CIFAR 10, VGG 16. So state of the art, I think, I don't know, but on top of my head, but it must be 99.99996% or something if you just do non-Bayesian. But this is because people started to use all this data augmentation and a lot of other tricks. Here we just took a plain VGG 16 and we did a comparison straight with other competitors and other ways of fixing prior. So people that didn't like Bayes' theorem started to do temperature scaling, which means effectively dampening the effect of the prior because they were not able to choose good priors. And so you see that there is a massive improvement in performance, which is almost 5% here. And the test log likelihood, we get better test log likelihood too. Same thing with some other more complicated model. And I think if you just do a GP on CIFAR 10, you get around 60% accuracy. I might be wrong, but that's a kind of figure. Just to say that in this case, using a powerful prior combined with a flexible model, which is in this case a convolutional neural network, and MCMC, gives us something which is quite good. I just wanted to leave time for questions, so I just wanted to give you maybe a one slide teaser about something else we did in this space. So we did the same thing for Bayesian autoencoders. As I said before, an autoencoder is just a neural network where you just have the input and the output to be the same, all right? And then you have typically a compression in the middle, which is denoted by this latent codes Z. just to do model compression, data compression. And you can think of this as a neural network in for an unsupervised learning task. And so again, same problem as before. We want to do a Bayesian version of this to compare it with the variational encoders. And I show you some faces so that we'll go straight to the point. Because now we are not working directly with variational inference, we can really separate out the modeling from the inference. So we can keep the model as the way it is. So it's a neural network. We treat it in a Bayesian way. And now we can do MCMC. Whereas if you do variational encoders, you're forced, your model and your inference are tied together. And so you cannot choose to do anything else. And so this is problematic when you start having low data, when you are in a low data regime. So in this experiment here, we only used 1,000 faces from this Celebay data set. And you can see that any variational encoders or GANs, in this case, well, this one works pretty well, actually. They don't really manage to get very good results, unfortunately. And the reason is that, again, they use little data. And so in this case, approximate inference might be the issue here. And so in our case, when we optimize these priors and then we do MCMC, we get faces that, so these are reconstruction, all right? And these are newly generated faces. So this works quite nicely. So we also have another one, but we changed a little bit the likelihood because here we have pixels, so we can do some sort of truncated Gaussian likelihood, whatever. Okay, I'm not going to go into the details. I think we use 1,000 faces to do the optimization of the prior, and then 500 to do the task of reconstruction and generating. All right, so that was just a teaser. So I think, I mean, if you work in Bayesian statistics, you know this, priors are important. And if you choose your prior in a bad way, you're putting a lot of mass into the parameter space in places where you should not be. If your prior is here and your likelihood is saying that you should be there, there is something funny about the way you chose the prior. Should you revisit the choice of the prior or not? I mean, this is open to philosophical debate if you want, but definitely, I mean, using any knowledge you have about the problem to be able to shift the mass of this prior, which was in this bad place in the parameter space, somewhere sensible is a good idea. And we know that. For a classification problem, you would like your prior to say a priori that all the classes are equally likely, right? If you have no idea about anything else, for example. And so the way we did it was to propose a new way of doing this using Wasserstein distance and sensible priors in function space. We showed that we have pretty good results in empirical performance, and we think I wouldn't want to brag too much about this, but I think we made a really a considerable step forward in showing that being Bayesian about parameters in neural networks is really something important. I mean, people have talked about this obviously, but now we have a practical way of actually showing this, right? So I'm really interested in a lot of problems where decision making matters, and applications in sustainability, I think, are something that I would like to move towards in the next few years. And we still haven't shown applications to massive scale problems. I think this is still missing, showing that we can do huge models, with now not only millions of parameters, but maybe tens or hundreds of millions of parameters, maybe even 1 billion of parameters, while still doing fully Bayesian inference. That's something interesting to try. And of course, you may wonder, well, if you have a lot of data, maybe you don't need to be Bayesian at some point because maximum likelihood is enough. But you never know when this breaking point is, right? So if you have more data, then you start thinking, oh, maybe I can use a bigger model. And then as you do that, then you go back into needing to be able to quantify uncertainty. What we're doing today, and this work will come out in archive maybe next week, in 2 weeks, we're actually trying to impose structural priors on latent codes in Bayesian autoencoders. So if you think about the Bayesian autoencoder the way it is, so randomness in the latent space is just due to the randomness in the weights. So now imagine that you want a particular distribution for your latent codes. For example, you want to model temporal data with an autoencoder. So you have a video, you want to do compression. So you would like your codes to evolve over time, maybe with a GP or something. So you would like to put a GP prior on your latent codes. But how do you do it? I mean, now you're putting a prior over the weights, and so that induces a distribution over the latent codes. How can you impose another prior for the latents? So actually, we have something that works extremely well for this, and this is going to come out in a couple of weeks. And people have done it already for variational autoencoders. For variational autoencoders, you already have a way to do GPs in the latent space or any weird priors you want. But for Bayesian autoencoders, this is still not out there. And so we're filling that gap. I'm also kind of intrigued by this idea of saying, well, now we have a lot of ways to do physics through ODE simulations. So a lot of problems in science are based on some physics, process of interest that we may describe with differential equations of computer models that are quite expensive. Imagine a climate model, for example. And so what we're looking at is ways to use these as ways to inform the priors of neural networks. So trying to merge a bit, physics with neural networks. All right. So these are the two publications that are associated with the presentation I made. So one is the Journal of Machine Learning Research this year, and this was a NeoRIPS last year on Bayesian autoencoders. And as I said, there is going to be another one coming up soon, in a couple of weeks. So thank you. Happy to take your questions.
Yeah, we have good time, so any questions?
Yeah.
How difficult was it, or rather, how stable was the optimization process?
Okay, I repeat the question in the microphone, maybe. How stable is the optimization? So we found that the optimization of the Wasserstein distance is usually quite nicely behaved. As you can see, these curves, I mean, these obviously are on a toy example, so they're not the same maybe as the ones that we see in like more complicated models. But the stochastic, we observe this stochastic optimization behavior where we have some good convergence, obviously a bit noisy, but we haven't found difficulties in optimizing this objective in general. So code is out there, by the way, so we would be happy for you guys to try and break it, So try it on whatever models you want and see for yourself. I mean, but generally, this has not been the most difficult part. Yeah.
To follow up on that, so does that mean that you don't have to tune learning rates?
Well, we still have to tune learning rates for this. I mean, there is a bit of I would say lack of automation as any optimization problem. You have to try maybe a step size and see, the convergence is a bit too slow, so maybe I can. But this generally is quite fast. Because again, you don't have data involved here. So it's only, it's data-free sort of optimization, if you like. So here, the inputs are the ones that you can choose a mini batch of inputs that you want to use to evaluate this difference in expectations, the Wasserstein distance, and then you resample the inputs every time. So that's where the stochasticity comes from. Yes.
Me or somebody else?
Yeah, you.
So, exciting work. So I was wondering then if you keep the motivation that you would, for instance, want to introduce ultimately some physics-based priors or really bring knowledge about the things that you are going to model, then that raises the question that why do you then have a neural network? And now, so the likelihood actually is not exactly what you want to have.
Exactly, yes.
That will then have some biases in the result.
Yes.
So of course, I understand why you are doing it, but I mean, is there some way how you can treat this in a more clever way than just thinking that is a proxy, and we don't fully understand what biases the proxy crosses?
Wonderful question. So the question is, how do we merge? First of all, why do we use neural networks to emulate what a piece of code is already doing? So one of the reasons is that there has been a lot of work on trying to do inference over these big climate models, for example, tsunami or earthquake models. You have parameters, you can simulate, and then you have some real observations. And so the question is, well, how do we optimize the parameters, or we do inference? It's a bit like what's happening with the differential equation models. You know, you have to iteratively sample different parameters, simulate, and get an output. You know, depending on how you treat the parameters, the Bayesian way or loss optimization, you have to optimize. And the problem is that you have to do this many, many times. And sometimes these climate models, for example, can take days just to obtain one realization of the output, to do one simulation. And so the question is, how can you do something which is data efficient, but also takes into account the uncertainty due to the fact that you don't have enough runs of the computer simulation? And so one idea is to say, well, let's use an emulator. So we've done it in GPs for differential equation models. We've done it for physics-based models in this calibration framework from Kennedy O'Hagan 2001. So there are many ways in which people have approached this problem. And the question is, well, if we now use a surrogate neural network that emulates what the code does, and we do parameter inference, well, we're biasing our inference over the parameters. Plus, there is this other issue that these computer models represent reality up to a certain degree of accuracy. So we should also account for this misspecification. And so one common way of doing it is to say, we have an emulator for the computer simulation, and plus we add some extra terms which account for this misspecification of the model. And now in light of real data, we try to infer both the misspecification part and the parameters of this simulator. And the problem is that this is obviously non-identifiable now, because we're introducing too many degrees of freedom in the formulation of the model. And as far as I know, in that community of computer calibration where people do this accounting of this misspecification, there's no way to solve this problem. I mean, people haven't solved the problem of non-identifiability. So I was hoping that maybe by looking at this physics simulator as ways to inform priors, could maybe be a way to recover some properties of identifiability, but I'm not sure. I mean, this is something I have, if anybody wants to collaborate on this, happy to do it. I have some ideas, but I haven't come up with a solution to that. But I think it's quite a nice way of thinking about this way of informing priors for neural networks, and a nice way to combine physics and neural networks in the same. Yeah. But I agree. I mean, this is a really important problem. How do we ensure that our estimates of the parameters in the end are something we can trust? And so in light of misspecification and in light of lack of infinite number of simulations from the simulator. Yes.
Very famous.
Thanks.
Questions. One question is actually about this slide.
Yeah.
Which is you have in the middle of this, if I understand correctly, hierarchical plan
Yeah.
is supposed to be more flexible.
Yes, exactly. Yeah, and this in the optimization, it happened to maybe hit a local minimum, and yeah, probably we just hit a local minimum, and the optimization just ended up in a place which is not that great. I mean, if you look at the value of the Wasserstein distance, it's quite large, and maybe we should have waited longer to make it. You know, sometimes these stochastic optimizations have a plateau, and then eventually they find a nice direction to go, and yeah.
The other question is about the sort of like the samples that you're using in order to compute the Wasserstein distance. So I remember from this function space BI papers, they tried a lot of things trying to do this in the setup of trying to approximate criteria.
Mm-hmm.
And it seems a bit like it always kind of like works half. And I suppose here's a bit different because you're interested in prior.
Yeah.
But I was wondering, like, you presented 3 different
Yeah.
ways and what you ended up using and whether you found anything like. I
don't remember which ones we use now in. I think we use something like the third option here. I'm not sure if I'm mistaken here. I should double check, but this is what I remember that we used, and it's we didn't find this to be so critical for this particular application. Like, how do we choose this set of points, not where we want to impose this, but yeah, in large dimensions. Yeah, that's why I was thinking that maybe some augmentation could help also to give more diversity to the lots. But I think in the end we ended up using something as simple as this. Yeah, but again, I think this goes back to the point of I was trying to make, that it's good to push yourself away from pathological stuff. And already something as simple as this, I think we need to maybe do a bit more study on this aspect. You know, how much do we need to optimize really in order for us to just be in a place where then data can do its job, right, properly, and the prior is not really pushing you to be still in a bad place. I think that's something we haven't explored. Yeah.
Okay, so I think we got a bit over time. So let's conclude the session. So let's thank the speaker again.
Thank you. I'm around, so if you have more questions, happy to.
Are there questions in chat?
Yes, there was a couple of questions. One was partially answered. Another was there any difference in running time between the gradient agency and mean field VI?
Well, we haven't. So with these new priors, we haven't really tried to run a variational inference. But it would be a good question to try to do it. I mean, field. I mean, it's quite fast, but also the quality in general of the approximation is quite limited, because you're really forcing yourself to. I mean, if you don't want to do mean field, then it quickly becomes expensive to do variational inference. So again, it would be nice to have these curves of computational time on the x-axis, accuracy in the y-axis. This is what I like to see all the time when I do comparisons of this kind, because you can see for how much you spend during your inference, how much gain you get in performance. And I think, I don't remember in the paper, we have a few of those, but I was trying to think if, yeah, we don't really, I think in this particular paper, we didn't do comparison with just plain like mean field variational inference or normalizing flow, variational inference with normalizing flows to give more flexibility. I think it would be interesting to have it. Yeah, it's a good question.
But just in kind of like order of magnitude, how does it compare against, let's say, just the default sample, like in terms of time?
Orders of magnitude more expensive to do this?
Yeah, and like here, like basically, what would be the other axis for that's still roughly, right? Like, so you get gain accuracy if you use your prior plus stochastic gradient MCMC, and well, how much kind of
I think we have these plots in the. I think we still show that we pretty quickly get good accuracy, with a few MCMC samples, and then obviously it takes a bit of time to then get, to keep improving. But I mean the difference in performance is, again, for this particular example, is quite marked. So I don't remember exactly now how the figure looks like, but I think there is a crossing point where maybe deep ensembles may be a bit faster at the very beginning, but then they plateau, and so then we get this curve that nicely improves on that. So yes.
Now you used stationary covariance functions.
Yep.
So do you think that stationarity is actually good prior?
Good question. I mean, in our case, we didn't. So, for example, for these image classification problems, we may think that might not be such a good idea, because now we're thinking about kernels where the inputs are images. So maybe you don't want stationarity. But again, I think it goes back again to the point where you would like to say, well, let's have something which has some behavior which is reasonable, at least a priori, and reasonable to the point where it moves away from these pathological priors, and then maybe more advanced kernels could do a better job.
Yeah, it seems like maybe the main benefit is getting better smoothing
Yeah.
prior, even if like stationarity, non-stationarity would not be
A deal breaker, yeah.
Yeah. Another one is then, like now there's better prior, but what is the role of activation function? Or we could think of like the basis functions.
Absolutely. Yeah, I think again it goes back to the point of how well can we approximate functions from any covariance, you know, with the GPU with any covariance, with any architecture, with any activation.
That's also like the choice of are the cases of the activation functions, are they stationary or non-stationary? Like Arno Solin had also one paper where intentionally using such activation functions that get the stationary behavior for neural network.
Yeah, absolutely. I think that's a good point. I think the way we were thinking about this is that someone comes to you saying, oh, I have this, my favorite neural network with this particular activation because I like it and it works so well. And now our job is to say, well, okay, let's make it Bayesian, let's make it work. And so we don't impose a way to choose activation functions. We are somehow imposed. That's the kind of scenario I had in mind. But obviously, if you can also play with that, I think there are ways in which you can determine that choosing an activation function determines certain properties on the. I mean, at least for shallow, it's easy, right? Well, easier. There is people, I think there are studies on that. When you start going deep, things become a bit more difficult. But definitely, I mean, if you have ReLU and you want to model something, infinitely smooth, then it's not going to happen. So yeah.
I wonder if you could model invariances with this sort of like augmentation. Like if you translate limits, you just move it around, or you rotate limits, you probably want the function to be invariant this time.
Yes.
So wouldn't you encode it using the Gaussian process for?
Absolutely, yeah, that'd be great. Yeah, I think it's a good idea.
Still like local, like small rotation, for example, it's like you know that it should like okay, currently it's smooth, so you know that it's smoothly changing the output. But I guess in this case it should just be flat. So you know that it shouldn't do anything.
That's true. Yeah. That imbalance is I mean, if you know how to impose them, yeah. Sounds good. Yeah, it's a good idea.
Okay, I guess we are done.
Great, thanks guys.